Hello everyone, this is a perfect video for understanding analytical techniques in chemistry. Today we are going to know about analytical techniques, NMR, and combined techniques. So today we are know about analytical techniques as it suggests that this is about ways in which we can measure or kind of analyze compounds and substances that we have produced, which is obviously very important in chemistry because we need to be able to identify what we have and what we don't have. So this topic really looks into a few different techniques, and we combine all of the techniques from year 1 and year 2. So analytical techniques used to identify compounds in chemistry. First of all, I want to start with thin layer chromatography, or TLC. Thin layer chromatography, you would have heard of chromatography before, and so this is basically a useful form of chromatography anyway. So this is way in which we can separate and identify colorless substances such as amino acids that have different solubilities. So normally when you have looked at say chromatography to paper and like paper chromatography or anything like that, you will have seen that get colored compounds, you see them migrate up the papers. So this is the ideal. They're not colored. For example, TLC uses a stationary phase of silica or alumina. So this is mounted on a glass or metal plate, so it's a little bit different. Got a pencil baseline is drawn to drops amino acid mixtures are actually added to the bottom, so it looks very similar to a paper chromatography setup. So what we do is we place the plate in the solvent. Remember, the baseline must be above the solvent line, so this line here has got to be above the actual line of the liquid. In the experiments, we can identify amino acids by measuring the positions in the chromatogram. Now, as I mentioned before, amino acids are colorless, so we can't actually see anything on the chromatogram. When we run this, we will just see a solvent has risen up. That's what we'll observe. So what we have to do is we have to spray a dye on it to try and identify or show up spots on amino acids that they have risen on the chromatogram. So we can use iodine or chemical colored 9-hydrin solution, or we can use fluorescent dyes and the UV light to actually identify what these are. After that, we need to dry and identify amino acids by calculating RF value. So RF value is calculating the RF value on the actual chromatogram, and then we use the RF value to compare them against the library of known RF values to help identify what amino acids we may have there. So let's have a look at the chromatogram. Obviously our sample, and this is after it's been run. We can see the spot has kind of risen up further up the chromatogram there. So this is the distance traveled by the spot in red, and this is the distance traveled by the solvent. So this is the solvent front at the top here, that's the baseline, that's where we started from. So the RF value, basically the distance traveled by the spot, which is this here divided by the distance traveled by the solvent, which is. So next chromatography is gas liquid chromatography, or GLC. Actually, it's really useful technique to separate a mixture of liquids that are quite volatile, and we can then identify them. So obviously compounds which are volatile and just done on, say, in normal air will just evaporate and you'll struggle to actually see the spots. So GLC helps to kind of get around that. So here is a GLC setup, and you can see that it's quite a big bit sits on a desk. In gas liquid chromatography, there have stationary and mobile phase. Stationary phase is column, and mobile phase is gas, which is inert, does not react with compounds. So GLC can be used to identify volatile compounds in oil paints, such as esters, and so can be used for suppose a less sinister use. Suppose in this example, we can say about painting and historians. We can identify type of pigments with GLC. Next device is NMR, nuclear magnetic resonance spectroscopy. We have two kind of analytical machines to identify carbon and the proton NMR. So carbon tells us about carbon-13, information on how carbon atoms are arranged, and they have got a high resolution. Proton NMR tells us information on how hydrogen atoms are arranged. We are going to look at both of them. So as you can see, this is the carbon NMR spectroscopy. We have two peaks because we have two different carbon atoms connected with each other. So red carbon is closest to the electronegative chlorine, and this means electron shielding is lower and the chemical shift is higher than in alkali group. The green carbon is further away from chlorine. This means the electron shielding is higher and the chemical shift is lower. So there have two different signals, which is circled in green and red. So next spectroscopy is hydrogen or proton spectroscopy. In proton spectroscopy, we have singlet, doublet, triplet, quartet, and multiplet. In NMR spectrum, we use peaks split into smaller peaks into splitting pattern. The number of smaller peaks corresponds to the number of hydrogen atoms and adjacent carbon plus 1, which is also known as spin-spin coupling. This rule is called the n+1 rule. So as you can see, there have three peaks in which is singlet, quartet, and triplet. So the singlet is OH group. It's always been singlet in OH. H in OH group. So CH2 is quartet because 3 hydrogens on neighboring carbon, and the triplet is CH3, which is 2 hydrogens in neighboring carbon atom. In this photo, we have 3 different spectra of unknown organic compound. Now we can identify a compound with these 3 spectrums. First is proton NMR, second is infrared, third is mass spectrometer. First of all, we can start with proton NMR. In proton NMR, we have 3 peaks, which is triplet, multiplet, and also triplet. And there have infrared spectrum. We can identify compounds by using data booklet. Next is mass spectrometry. In mass spectrometry, we have last peak, which is the M+ peak, is the molecular mass of the compound. So as you can see, in this peak we have MR of the molecule is 58. As you can see, we have last peak at 58. It tells us MR of this molecule. The previous peaks are fragment peak, like C2H5+, and so on. The next spectrum is infrared spectrum. Infrared spectrum is essential by identifying functional groups in the compound. So as you can see, there have peak at 1750. So it's likely to be caused by vibrating C double bond O functional group in the compound. So it will be aldehyde, ketone, or ester. So finally, there is proton NMR spectrum of the unknown compound. We have, as I said before, we have three peaks: triplet, multiplet, triplet. Triplet means that there have four hydrogen atoms in neighboring carbon atom. Multiplet is more than four hydrogen atoms in neighboring carbon atom. So triplet is three hydrogen atoms in neighboring carbon atom. So all given informations, we can identify the compound. It's propanol because the mass spectrometer tells us the substance has a molecular mass of 58. The infrared spectrum confirms that there is a C double bond O group. However, there are no other peaks to suggest any other functional group present. NMR confirms that the C double bond O group is part of an aldehyde group. So NMR also confirms a CH2 and CH3 group, which, when supported with the mass spectra information that the molecule has a MR of 58, we can build our mystery molecule. It is the propanol.